National Electrical Code Section 250.24b addresses the grounding of service equipment enclosures. It states that service equipment enclosures must be grounded according to Section 250.30, which deals with grounding requirements for services and service equipment. However, Section 250.24b does not specifically mandate the presence of a grounded conductor within these enclosures. If the electrical system solely comprises line-to-line loads, a grounded conductor is not essential for either safety or the correct operation of the system. The necessity for a grounded conductor arises only when line-to-neutral loads are present. In this scenario, it is permissible to terminate the grounded conductor within the main distribution panel, or MDP, without establishing a connection to the service disconnect. This approach allows for future integration of line-to-neutral loads should the need arise. The function of a grounded conductor, often referred to as the neutral, is multifaceted. Firstly, it provides a stable reference point for voltage within the electrical system, ensuring that line-to-neutral voltages remain balanced and within acceptable limits. Secondly, it offers a low impedance path for fault currents to return to the source, facilitating the rapid operation of overcurrent protective devices such as circuit breakers and fuses. This is particularly important in the event of a ground fault, where a live conductor comes into contact with a grounded surface. Thirdly, it mitigates the risk of electric shock by maintaining the grounded parts of the electrical system at or near 0 volts relative to ground. The absence of a grounded conductor in a system with only line-to-line loads does not compromise safety, provided that the equipment grounding system is properly installed and maintained. The equipment grounding system consists of conductive pathways that connect the non-current carrying metal parts of electrical equipment to the grounding electrode system. This system ensures that any fault current will flow back to the source, tripping the overcurrent protective device and energizing the circuit. The grounding electrode system, in turn, consists of one or more grounding electrodes that are bonded together to form a low-impedance connection to the earth. Common grounding electrodes include ground rods, ground plates, and metal water pipes. When installing a service without a grounded conductor, it is crucial to ensure that all equipment is properly grounded in accordance with the National Electrical Code requirements. This includes bonding all metal enclosures, raceways, and equipment frames to the grounding electrode system. The size of the grounding conductors must be adequate to carry the maximum fault current that could occur in the system. Refer to National Electrical Code Table 250.122 for the minimum size of equipment grounding conductors. It is also important to verify that the overcurrent protective devices are properly sized and coordinated to protect the electrical system from overloads and short circuits. The selection of overcurrent protective devices should be based on the ampacity of the conductors and the characteristics of the loads being served. Furthermore, regular inspection and testing of the grounding system are essential to ensure its continued effectiveness. This includes visual inspection of grounding connections for corrosion or damage, as well as testing of the grounding electrode resistance to ensure that it remains within acceptable limits. A high grounding electrode resistance can indicate a problem with the grounding system that needs to be addressed. In summary, while the power company may provide a grounded conductor, National Electrical Code Section 250.24b does not mandate its connection to the service disconnect in a system with only line-to-line loads. The grounded conductor can be terminated in the main distribution panel and reserved for future use, provided that the equipment grounding system is properly installed and maintained. This approach ensures the safety and reliability of the electrical system while minimizing unnecessary complexity. Moreover, the decision to omit the grounded conductor in a system with only line-to-line loads can offer several advantages. Firstly, it simplifies the wiring and reduces the number of connections required, potentially saving time and materials. Secondly, it eliminates the possibility of neutral current flowing on the grounding conductors, which can cause nuisance tripping of ground fault circuit interrupters or arc fault circuit interrupters. Thirdly, it reduces the risk of voltage drops on the neutral conductor, which can affect the performance of sensitive electronic equipment. However, it is crucial to carefully consider the potential drawbacks before deciding to omit the grounded conductor. Firstly, it may limit the future flexibility of the electrical system, making it more difficult to add line to neutral loads later on. Secondly, it may increase the impedance of the ground fault current path, potentially slowing down the response time of overcurrent protective devices. Thirdly, it may require more sophisticated grounding techniques to ensure adequate protection against electric shock. Therefore, it is essential to consult with a qualified electrical engineer or contractor to determine the best approach for a specific application. They can assess the specific needs of the electrical system and recommend the appropriate grounding configuration. In addition to National Electrical Code Section 250.24b, there are other code sections that may be relevant to the grounding of service equipment. National Electrical Code Section 250.20 specifies the conditions under which electrical systems are required to be grounded. National Electrical Code Section 250.30 provides detailed requirements for grounding alternating current systems. National Electrical Code Section 250.50 covers the grounding electrode system. National Electrical Code Section 250.104 addresses the bonding of metal water piping systems and other metal parts. Understanding these code sections is essential for ensuring that electrical systems are grounded safely and effectively. Furthermore, it is important to be aware of any local amendments to the National Electrical Code that may be in effect. Local jurisdictions may have additional requirements for grounding that are not included in the National Code. Therefore, it is always best to consult with the local electrical inspector to ensure compliance with all applicable codes and regulations. The grounded conductor, often referred to as the neutral, plays a critical role in electrical systems that serve line to neutral loads. It provides a return path for current to flow back to the source, allowing the circuit to operate properly. Without a grounded conductor, line to neutral loads would not function. The grounded conductor is typically connected to the neutral point of the transformer or generator that supplies the electrical system. This neutral point is also connected to the grounding electrode system, providing a low impedance path for fault currents to return to the source. In the event of a ground fault, the fault current will flow through the grounded conductor back to the source, tripping the overcurrent protective device and energizing the circuit. The grounded conductor is typically identified by a white or gray color. This color coding helps to ensure that the grounded conductor is properly identified and connected throughout the electrical system. It is important to never use the white or gray color for any other conductor in the system. The size of the grounded conductor must be adequate to carry the maximum unbalanced load that could occur in the system. The unbalanced load is the difference between the current flowing in the phase conductors and the current flowing in the grounded conductor. National Electrical Code Section 220.61 provides guidance on calculating the unbalanced load for service and feeder conductors. In some cases, the grounded conductor may be intentionally omitted from a circuit, such as in a three-phase, three-wire system. However, this is only permitted under certain conditions and with specific precautions. For example, the equipment must be double insulated or supplied from an isolation transformer. In conclusion, the decision to include or omit a grounded conductor in an electrical system depends on the specific application and the types of loads being served. When line to neutral loads are present, a grounded conductor is essential for proper operation and safety. However, when only line-to-line loads are present, the grounded conductor may not be required, provided that the equipment grounding system is properly installed and maintained. It is always best to consult with a qualified electrical professional to determine the best approach for a specific situation. They can assess the specific needs of the electrical system and recommend the appropriate grounding configuration, ensuring compliance with all applicable codes and regulations. Furthermore, it is important to remember that electrical codes and regulations are constantly evolving. It is essential to stay up to date on the latest changes and interpretations to ensure that electrical systems are designed and installed safely and effectively. This can be achieved through continuing education courses, industry publications, and participation in professional organizations. By staying informed and engaged, electrical professionals can help to ensure the safety and reliability of electrical systems for years to come. The information provided here is for general guidance only and should not be considered a substitute for professional advice. Always consult with a qualified electrical engineer or contractor before making any decisions about the design or installation of an electrical system. They can assess the specific needs of the application and recommend the appropriate solutions, ensuring compliance with all applicable codes and regulations. Remember that electrical work can be dangerous, and it is important to take all necessary precautions to protect yourself and others from harm. Always de-energize circuits before working on them, and use appropriate personal protective equipment such as gloves and eye protection. By following these guidelines, you can help to ensure that electrical work is performed safely and effectively.